Welcome back to Bite-Sized Breakthroughs, the podcast dissecting the latest and greatest in the world of AI. Today, we're diving into a paper that tackles a crucial challenge in the realm of large language models, or LLMs for short, memory efficiency. That's right, Alex, and I'm thrilled to be joined by Dr. Paige Turner, a leading researcher in the field, and Prof. Wide Spectrum, a renowned expert on the broader implications of LLM development.
Thank you, Alex. It's great to be here. My pleasure to join this conversation. Let's unpack this memory challenge page. Can you explain why training LLMs is such a memory hog? Sure, Prof. Spectrum. It's a combination of factors. LLMs have become incredibly large with billions of parameters, basically the connections that determine how the model learns and operates. These parameters, along with their gradients, which are used to adjust those parameters during training, require massive amounts of memory. Then there's the optimizer state, which stores information like the momentum of the updates, and those can be even larger than the parameters themselves.
So we're talking about a memory-intensive process, and this is a big barrier for researchers, especially those with limited resources. Is that why this paper is so exciting?
Exactly, Alex. This paper introduces a new approach called gradient low-rank projection, or GaLore. It's a breakthrough because it allows researchers to train LLMs with full parameter learning, meaning the model can explore the entire space of potential solutions while being much more memory efficient than existing techniques.
That's quite a claim, Paige. Can you explain how GaLore works?
Sure. Instead of trying to make the weight matrix itself low rank, which has been the approach on previous techniques like LoRa, GaLore takes advantage of the fact that the gradient, which is used to update the weights, tends to have a low-rank structure during training. This means the gradient can be effectively represented by a smaller set of values.
Can you clarify what low rank means? It sounds like a pretty technical term.
Great question, Alex. Imagine a matrix, like a spreadsheet. The rank of the matrix is essentially the number of independent rows or columns. A low-rank matrix has fewer independent rows or columns, so you can represent the entire matrix with a smaller set of values. This is where the memory savings come in.
That makes sense. So GaLore essentially compresses the gradient, enabling the use of less memory during training. But how does it maintain the full parameter learning potential?
That's the clever part, Alex. GaLore doesn't just project the gradient onto one low-rank subspace. It dynamically switches between multiple subspaces throughout training. This allows it to explore different directions of the gradient and ultimately learn the full range of parameters.
It sounds like GaLore is doing a lot more than just compressing the gradient. It's also adding a level of flexibility and adaptability to the training process.
Exactly, Alex. That's what makes GaLore a significant step forward. It combines the efficiency of low-rank methods with the power of full parameter learning.
I can see how this could be a game changer. But before we delve into the experiments, Paige, can you explain how GaLore compares to existing low-rank methods like LoRa? They also try to reduce memory, right?
That's right, Alex. LoRa is a popular technique for parameter-efficient fine-tuning, where you take a pre-trained model and adapt it to a new task with minimal changes. It does this by adding low-rank adapters to the frozen pre-trained weights. However, LoRa has limitations, particularly when it comes to pre-training models from scratch. It often needs a full-rank training warm-up phase, meaning you have to train the model initially with all parameters active before switching to the low-rank representation.
So GaLore is a more streamlined approach for pre-training. It doesn't require that extra step?
That's correct, Alex. GaLore can pre-train models efficiently without any kind of warm-up phase. And because it's working with the gradient, it doesn't alter the training dynamics in the same way as LoRa, which can sometimes lead to performance issues.
Prof. Spectrum, what are your thoughts on this comparison? How does GaLore fit into the broader landscape of LLM training techniques?
Well, Alex, GaLore is a significant addition to the toolbox of LLM training techniques. It offers a compelling combination of advantages. By focusing on the low-rank structure of the gradient, it addresses the memory challenge in a way that's both efficient and adaptable. It also offers more flexibility than existing methods like LoRa and ReLoRa, which require more complex configurations. This move away from manipulating the weight matrix itself and focusing on the gradient is a subtle but important shift in thinking about LLM training.
It's fascinating how this research highlights the importance of understanding the dynamics of the training process itself. But let's move on to the experiments page. Can you tell us about the setup and what the results showed?
Of course, Alex. The experiments were conducted on a large scale using various model sizes from 60 million parameters up to 7 billion parameters. They trained these models on the C4 dataset, a massive collection of text data, and evaluated performance using measures like validation perplexity, which is a way of assessing the model's ability to predict unseen text.
So, the bigger picture here is that they tested GaLore on a range of models to see if it scales well. What were the key findings?
Yes, Alex, and the results were quite impressive. GaLore consistently outperformed existing low-rank methods and achieved performance comparable to full-rank training, but with significantly less memory usage. In fact, GaLore achieved up to 65.5% memory reduction in optimizer states while maintaining performance, which is a remarkable improvement.
That's incredible. And what about the practical implications? Did GaLore enable training larger models on more accessible hardware?
Absolutely. GaLore enabled the authors to train a 7 billion parameter model on a single GPU with only 24 gigabytes of memory, which is remarkable. Previously, this would have been impossible without using expensive model parallelism techniques or memory offloading strategies, which can be complex and time-consuming.
That's truly a breakthrough. So it's not just about reducing memory, it's about expanding the potential for training larger models, especially for those who don't have access to massive computing resources. Prof. Spectrum, what do you think of this particular finding?
This is a critical development, Alex. It has the potential to democratize LLM research and development by making it feasible to train large models on more readily available hardware. We can enable a wider range of researchers and developers to contribute to this field. It can also lead to more widespread deployment of LLMs in applications that were previously limited by resource constraints.
That's a very powerful point. Paige, can you discuss the limitations of GaLore? Because no method is perfect, right?
You're absolutely right, Alex. While GaLore is a significant step forward, it does have some limitations. The current implementation introduces a small overhead in throughput compared to some other memory-efficient training techniques. The theoretical analysis also relies on certain assumptions, such as the specific gradient structure and Lipschitz continuity of the weight matrix. It remains to be seen how well GaLore generalizes to other types of network architectures and loss functions. And while GaLore demonstrates its ability to train a 7B model on a single GPU, its scalability to even larger models needs further investigation.
This is a common theme with cutting-edge research, Paige. There's always more to explore and improve. But even with those limitations, GaLore seems incredibly promising. Can you share some of the exciting future directions for this research?
Absolutely, Alex. One promising direction is to explore the application of GaLore to other model architectures beyond transformers, such as vision transformers and diffusion models. Another avenue is to develop even more efficient projection matrices through low-memory parameterization and quantization techniques. We can also investigate the feasibility of elastic data distributed training using GaLore on consumer-grade hardware with limited bandwidth. And finally, we can explore integrating GaLore with existing memory-efficient techniques, like fused backward operations, to further enhance memory efficiency in large-scale pre-training from scratch.
It sounds like there's a lot of exciting potential for GaLore to contribute to the field of LLM training in the years to come. Professor Spectrum, any final thoughts on the broader implications of this research?
I think GaLore is a prime example of how focusing on the underlying mechanisms of training can lead to significant breakthroughs in LLM development. It shows us that there's always room for innovation and improvement, even in a field as rapidly advancing as AI. This research has the potential to not only accelerate progress in LLM training, but also make these powerful tools more accessible to a wider audience.
That's a perfect way to sum it up, Prof. Spectrum. Thank you both for joining me on this journey into the fascinating world of memory-efficient LLM training. I hope our listeners have gained a deeper understanding of GaLore and its potential to reshape the future of AI. Don't forget to subscribe to Bite-Sized Breakthroughs for more insightful discussions and groundbreaking discoveries in the world of AI.